So I've been doing applied cryptography for 30 years and a lot related with fast implementation of cryptography in the good old days. I was one of the people participating in the AES competition, did elliptic curves very fast, with a lot of work on side channel attacks. Um, and then maybe 10 years ago, I started looking in hardware Trojans, very exciting work there. And in parallel, also for the last 10 years, part of my group started working on this totally different type of applied security, namely physical layer security. So essentially what we're doing, we're using Wi-Fi signals for security applications. And that's what I want to talk about. And, that's why it's a sketchy type of cybersecurity between hardware and software, because we're using electromagnetic waves. Okay, so how do I get to the next slide? Okay. Oh, it doesn't show here, right? I think I probably have to go to a different thing. I have to go to here. Okay, here it comes, right? Yeah. So, if German professors do great things, it's always the PhD students, right? It's probably very different in the US. So, in particular, grateful by Paul and Johannes in particular. Much of what I'm going to present today was the PhD thesis of Johannes a couple of years ago. But we closely worked with Alex and Sebastian from Princeton University. They're not security people, so they worked in, roughly speaking, nuclear disarmament, which is very interesting, right? Okay, so where are we? So there's all these different things, right, in cryptography, and you guys know that very, very well, right? And there are all these different aspects of modern cryptography, right? And essentially, they developed many methods that are very proven, right? Sometimes it's hard to get them to adaption, but theoretically, these things solve really nice and interesting problems, right? But they all, and that sounds like a very weird statement. What are they made for? Well, they work in the digital domain, right? So we implicitly assume we have a laptop, we have a smartphone, we have an ARM processor, we have an IoT device, whatever, right? But they also, and I'm going to talk about that, many problems that are security relevant, they are not limited to this digital artificial domain, right? We're going to see a few examples, right? Is this very new? It's not really. There's a brief history of this physical layer security. Initially, these were people that grew out of the information theory community, right? There was Shannon, right? Shannon came up with the wiretap channel, and Weiner picked that up later. Then were Uli Maurer and Arsvet and Cesar, and they talked about how can we do key generation from public discussion, which is essentially some kind of channel parameters. And then Hershey, not that long ago, maybe 30 years, right? So he came up with wireless key generation. People were really excited about that, right? And what you do here, really, you look as really communication engineering aspects, such that as the properties of the wireless channel, right? You do signal processing and you do a lot of channel coding. These things, right? This is engineering. Actually, my bachelor was in communication engineering. That's this type of stuff, right? So an intuition, so this is roughly the setting of the wiretap channel, right? So you have Alice and Bob, they talk, and then it's encoding and decoding in order to get bits over, right? And now the intuition is if you have an eavesdropper, he might get channel access, but he doesn't have the identical channel because he has a different location as Bob, right? So if Bob and Eve are the same, right? So, and now the intuition of this wiretap channel is that we somehow leverage this difference, right? By code, primarily based on coding methods, right? In practice, these things never really work really, really great. We did some work on that, right? But maybe more importantly, right, in applied cryptography, now you can do key exchange, right? Well, as the young guns, there are much better ways of doing key exchange. Why should we go through that pain and do that, right? With very questionable security assumption, right? So, and now the not very deep paradigm here is use physical layer security for applications where digital don't work, right? Don't try to replace Diffie-Hellman key exchange or elliptic curve, Diffie-Hellman, whatever, right? RSA, right? What's Christof talking about, right? There's actually quite a few applications. I want to give you some security applications that involve our environment. Big thing is tamper detection, right? How do you, for instance, there was this big paper by, or line of a string of paper by Ross Anderson around the turn of the millennium, where he showed if you take a payment terminal at a gas station, right, where you put your credit card in, if you can put in a little needle and probe that, the whole thing can be broken, right? And that makes sense by intuition, right? Because these digital systems are designed so that you assume there's no physical attack. An attacker cannot read out key bits or whatever, right? Part of the internal communication.
Or being stuff or tamper for like breaking the functionality.
Well, mainly here for reading. So that was, but there are all kind of different things. But yeah, I think my mental model is you put in a needle somewhere and you try to probe some internal state of an algorithm of a protocol, this type of thing. And kind of course, then it breaks, right? This type of thing, right? There's a relatively new line of research, and we're part of that circus is if you want to do privacy violation with a very simple example, it's not that hard because we have Wi-Fi here, right? I just turned on my laptop and I got connected with the Roam, right? If people outside the street pick up the strength of the Wi-Fi signal, it will vary whether I move in the room or not, right? Because I changed the Wi-Fi thing, right? And people don't have to break AES, right? That's encrypting this. It's just looking at the Wi-Fi waves essentially as radar signal, which is very different from, I'm sending email or my presentation is being sent out here, this type of thing, right? So this is another thing, which is a privacy issue, which has to do with the physical space. Has nothing to do with cryptographic protocols, right? How do we deal with that? Then there's virtual proof of reality. There are many more. And I'm going to talk about virtual proof of reality, which is kind of an exotic topic that was, I think, that was coined by Uli Rührmeier, a German security researcher. And we found a really nice application for that. Okay, so what are we? Very wild application, right? We look at nuclear warheads. These are nuclear warheads. There's a guy. So they're like the size of a big American refrigerator, right? Very macroscopic things, right? As you will see in the next slide, many of these nuclear warheads are in storage, right? And it's quite critical to monitor them. That means that the Americans make sure that actually the Russian warheads stay in storage and vice versa, right? Okay. And so the security question is very much security, right? World peace, right? If we want to remotely verify whether these nuclear warheads are untouched, right? Whether they're still there. Going to give you. So this is all, and we learned that all from our friends in Princeton, right? It's this public stability institute, right? So what you see here, this the number of nuclear warheads in the world, right? Both Russia and the US, they have around between 5,000 and 6,000 nuclear warheads, right? The red ones, we are kind of safe because they're covered by the New Start treatment. Like dinosaurs that, like me, we remember that was a big thing, during the Reagan eras, right? So they are actually mutually monitored. They're actually, I didn't know that before we started doing the projects. They're actually Americans flying to Russia, looking whether they're still in place and vice versa. So this is part of it, right? What we didn't know is this one, which are actually more, right? So these are non-deployed systems. They are typically, that's my mental picture, deep in some silos in the Ural Mountain in the middle of Russia, right? Very well hidden, right? And one big problem is, are the 2,815 nuclear warheads actually still in the silos, or they're secretly mounted on nuclear warheads, submarines? Same goes with the 2,000 US missiles, right? So how do we deal with that, right? Okay. So this is a very simple picture, right? So now we start talking about crypto-ish thing, right? So the prover, the Russian colleague, has to prove to his American colleague, these are the warheads, they're still there, right? How do we do that? Well, what is really, really nice, and what is that? Yeah, they're still there. What's the problem, right? Maybe, right? How do we do that? And by the way, super hostile environment, right? When we started working on that, because we applied people and we talk about code breaking, said, so what is the budget, right, of the adversaries? And they're like, well, annual budget of Russia. It's not like renting Amazon Cloud, right? This is whatever. It's crazy here, right? So the one of the first basic mechanism is you can use RF wave, and actually we did a lot of experiments, and you literally go to eBay, you buy a $19 router, but you're not sending messages, you just use the RF signals to take a fingerprint of that, right? You look at, maybe two antennas are sending, two are receiving, and then it turns out that all the signals are quite sensitive to every single nuclear warhead, right? So if you move with one of the warheads, the fingerprint would change because the reflection changed in here, right? So now the idea is you get this fingerprint R out, which is somewhat the pattern of, the radio waves bouncing around in the room, right? And now the prover sends this over. And just you're going to see like in 10 slides from now, I'm going to show you if you move one of these warheads by 1 millimeter, which is 1/32 of an inch, right? If you're not used to it. So very minusculely, you can detect it very reliably. So that works pretty nice, right?
Is this cells being connected to this router?
No. They're standing there. Router is up on the roof. This is just radio waves. They're bouncing around. You're sitting out and this blah, 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 and then it arrives there.
Oh, so it's like very simple.
Very simple setup. Again, you buy that literally for $19. You put it up. This is sending, this receiving. We could do that here. And everybody, if you would move your water bottle, yeah, that would be there. Very surprisingly sensitive. So the basic technology is great, right? So again, it's like if you wish to take like a radar print of the room, right? Very easy, right? You don't have to pre-adjust anything, you just do that, right? Sure.
From simulate the environment and is one of the ones.
That is the rest of my talk. Very good. Yeah, very good. Right. So this is the basic setup. In a different setup, if you just want to monitor your garage, whether your car got stolen from your garage, is solved, right? But now we have this guy, right? The Russian has control over the rooms. He tried to manipulate it. This is what we need to talk about. Okay, very good, Chris. Okay. So, and now the problem is, this is the setting we worry about, right? Some of the warheads getting removed. Americans would like to detect that. Russians would like that this is not being detected. This is a setup, right? So the first thing that happens, the fingerprint changes, of course, because 4 of these big American refrigerator things are missing, right? So there's different reflection. This will definitely be different, right? But now the Russian is not dumb, right? The attack happens by replay, right? The Americans waiting for that. I'm going to show them, right? Everything's fine, right? So this is not very deep, this type of attack, right? So what's missing here? Freshness, right? What do we do? Challenge and response, right? This is what, if you go to the ATM machine and you get $50 out, right? With your lead cash, right? Which we're not doing anymore, but in the good old days. Yeah. So, and now I have to talk about this because now it's get complicated to get that, right? How do we get freshness? And the freshness is not this like digital, we do in crypto type of thing. We need some kind of fresh versions of this room with respect to these radio waves that are bouncing around, right? So we have to, let's see how we do that. Well, and now I always really wanted to study mechanical engineering. I never did. So we built we need a challenge generator, but the challenge generator has to fiddle around with the radio waves, right? So this is not an IoT arm something, but this machine, I don't know, this is like pretty much my size, right? This is aluminum, and you have a lot of little mirrors that turn. You get better picture in a second. A lot of little mirrors, and the mirrors somehow reflect the radio waves differently in that room. Yeah, so that's our setup. So this is one of these shipping containers, 20 feet, right? It's actually standing in the basement of the building where you were, right? It's like the really down, something like 20 feet underground, right? And this is a machine in the background. We have a lot of money at Max Planck, but they didn't allow us to buy nuclear warheads, so we bought one of these blue barrels for 49 euros in the hardware store. So that's the setting. Okay, that's the setting. This is what we built. The two core components in this machine that we built. This is an aluminum box. It's about maybe a feet long, maybe a little smaller. It's cubic. And you have two antennas. One is sending, one is receiving. And why is that a good setup? Because what we want, so this, let's say, is the sending antenna. It's sending a signal out. The walls are metal, so everything is bouncing back and forth. The receiving end is on the other side of this cube, right? So it's kind of hard for the wave to get there. The wave first has to bounce in the room. Bouncing is good for us, right? We want to have many bounces, but then eventually it comes back to it, right? So this is this first, and we built that ourselves, right? Yeah, so this is the roughly the frequency range that you have access to with Wi-Fi signals between 2 and 9 gigahertz. The other thing is, and that was essentially the setup before. Now we need this challenge generator, right? So what we do, these are little stepping motors, right? That things they have 200 positions, so every 2 degrees roughly. And then they have this aluminum thing on it, right? Just aluminum is about this high, maybe, right? And that's why it's maybe 3 inches by 8 inches, something like that. And that exists in the literature. This type of shape is what communication engineering people use to essentially introduce randomness to an environment. So this is not our invention, right? Okay, and so what you see here is, and what we call a challenge, and this is a weird thing, right? The challenge is now, because we have 20 of these mirrors, 1, 2, 3, 4, 5, 20 of these, right? Every challenge is that you set these 20 mirrors in some position, typically a random position, right? How many positions do we have? 20 mirrors, 200 positions is about 2 to the 150. So it's a huge space, right? And this is what we call a challenge, right? So this is kind of a physical setting of these little mirrors, right? And then the response is what the antenna gets. So the one antenna that always sends is the same signal. So this is not communication. There's zero information in that signal itself. You just do an Dirac pulse, right? Here's what the other antenna receives: frequency, and this is magnitude, and you see challenge C0 with some setting of the mirrors. C1 is some other random setting of these 20 little mirrors, right? And it's actually fun to see, it makes a little noise like a little robot, and then they adjust. What you see here, these signals are different. That's what we expect, right? Also, what's nice is in a fairly sensitive matter. So if you only switch one mirror, a lot of things change, right? Okay, now it's getting interesting. So how do we turn that into a useful protocol that keeps the world a safer place, right? So you have 2 phases. Phase 1 is the setup phase, and it's just as an example, let's say 1 day. The setting is, and that's a big if here, right? The Americans get access to the Skyline router for 1 day, right? They can come in with their measuring equipment, right? And what they do is they feed in one challenge. Again, one challenge is one randomly setting of the 20 mirrors. It takes like a millisecond, so 5 milliseconds, right? And then one antenna sends the pulse, the other antenna records, and this is I. This is 14. Okay, this is the response. You do that once. C2 is the next random number that sets the 20 mirrors in another random position. You get another RF fingerprint. So this is an RF fingerprint, this is an RF fingerprint, blah, 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 blah. You can roughly do that with our setup. You can collect something like 100,000 samples in 24 hours. Maybe you can do 1 million, but this is the order of magnitude. No, it's not. No. Here's a laptop, right? The laptop sets the mirrors. Tick.
Okay.
Message. Tick. Message. That's what we do, right? We did a lot of that. Later, actually, the fun thing is talking about how to attack that system, and then you need many. You need ML. Will be ML. Okay. This is phase one. Americans say thank you, my dear Russian colleagues. They collect the database essentially here, right? One memory stick with, let's say, n is 100,000, right? They fly back to the Pentagon, right? Now comes the interesting thing, the proof phase. And let's say we want to do that for 1 year, right? So you measure for 24 hours, and now for 1 year, you can monitor this nuclear warhead silo in Russia, right? So what the Americans do, the first time they send challenge C1, that means now the Russians have to put the mirrors in exactly that position that the Americans did initially, right? First setting, right? So they do that here. The Russians sent back R1 prime, right? And now the Americans look, is this R1 prime, is that close enough to the R1 that I recorded in this 24 hours that I was in Russia, right? So, and now don't reuse, right? Because now at this moment, the Russians know R1 prime. They know if this challenge comes, this is a response, right? Well, this is being crossed out from your database, right? And then let's say 10 seconds later, the Americans send C2 over and expect the fingerprint output that matches this. Do that over and over and over again. And here in our example, if we start with 100,000, this lasts roughly for 1 year. This is important, right? We're going to talk about, yeah. Let me first talk about, any questions so far? You look, yeah.
The question, why would it be, so you mentioned it might be slightly different, R1 prime. Is that
because of noise? Because of noise.
Or no?
Yeah, I'm going to talk about that. Yeah, it's noise. Things are not ideal, right? Even if this is not digital. So even if let's say what the Americans do, you send C1, you set the mirror position, you said, give me the fingerprint, you measure the fingerprint. If you do the same thing 5 seconds later, R1 is not quite identical on an analog level.
If nothing else,
It's like the air molecules or
air molecules, it warms, yeah. I mean, the measurements itself are noisy, this type of thing, right?
so it's there for completeness.
We'll see in a second yeah, it's a good question. Yeah, so this is the whole setup again, right? This is roughly my height, right? This is like 5 feet something. Here are the mirrors, the stepping motors. What's it? Yeah, it's cute. Yeah. So okay, and now we talk about actually really interesting is it to talk about attacks, right? This is what we love, right? Okay, and there are essentially 4 properties you want to look at, right? Temperament detect, that's the main thing, right? Really, what would the Russians do? Is that long-term stable? It's a big engineering issue. What is really the challenge, the key space, if you wish, right? And then a big thing is ML attacks, because it's the efficiency thing to do here. Okay, so this is what I just discussed. So, you would think, as being, we are all digital people, right? You take one fingerprint, you take one fingerprint again, 5 seconds, you would get the same response. And varies a little bit, right? So we take the Euclidean distance, which is some kind of measure that looks how much do the fingerprints differ. Well, they're not identical, right? I mean, this is life, right? This is life. And this is a fancy term. This is the intradistance. Between one challenge, right? You use one challenge 2 times, 3 times, 4 times, 5 times. How much will it differ? For a little bit, right? What is really interesting is now what happens the interdistance. So now we take, this is challenge one, used 1, 2, 3, 4, I don't know, 50 times maybe for this plot. Now we take a different challenge. That means different, again, challenge is different mirror settings, right? Or randomly different. That means all 20 mirrors take different positions. On average, you get this. This is nice, right? So this is now the interdistance between different challenges, right? And now you do simple statistics, right? And this is the threshold. This was like 2 years of work, right? To end up with here, right? To get the equipment, you know. I mean, we're not communications people, right? Then we always use equipment that was too expensive, but with Max Planck, then we bought really expensive measurement equipment, and suddenly it works, right? So, okay, so this is great, right? So that makes sense here. So what about temper detection, right? So what we had in this setup is we put one of the drums on a plate, and the plate can be moved very slowly, right? And then what you see here, this is the drum displacement in millimeters. So this is 1/10 of an inch here, right? Millimeters, right? And the question is, so we start here from 0, now we start to replace it, and this is the old threshold we had before, right? So what happened? And it turns out almost exactly with a 1 millimeter displacement can be detected. This is pretty nice. And again, the attack is not that they are moving the nuclear warheads, you know, to sweep dust underneath, right? To take one of these big refrigerator-like things out, right? So again, this is surprisingly sensitive. We did a very different, it was actually a S&P paper 3 years ago. We used the same for similar technology for detecting temper attacks against server racks. And we could detect a needle that was 1/10 of a millimeter, which is like you can barely see, right? It's like, you know, getting like the thickness of a human hair. So using RF as radar is a good idea. That's what I'm saying.
Is this what you expected when you started, or is this what you thought?
We didn't really. I mean, we didn't have much expected. I think it works better than we thought, right? We're also lucky that this whole setup puts it in a metal room with little metal mirror works surprisingly well. Actually, we tried. The stupid thing about this is it looks cool. It's a mechanical system. It's also very stupid. You don't want to have a mechanical system, you know, that age, blah, 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 blah. So we tried to replace it with some kind of digital adjustable surfaces that reflect, and they don't work very nice. So there's we kind of the basic mechanical design. We were really lucky. So we had to let's do that, and it's, you know, Christian, actually previous PhD student Christian Sanger suggested that. Are you sure, Christian, you want to do that? So we were lucky with this type of setup. And I'm going to talk in 2 or 3 slides about attacks, and then you need ion nonlinearity, and that's what we get with this here, which is something you don't see at the moment, right? Another very much engineering thing is what is the drift over time, right? In aging, and what you see here, so this is the intradistance, it changes over the course of a month, right? 28 days is fairly stable, right? So we are safely away, right? And again, so the most expensive thing was like a measurement equipment for the antenna signal, and there was something like $20,000. I mean, if Pentagon decided to build that, you know, they spent probably 500 million on that, right? And that would probably be dead flat here, right? This type of thing. So it's always, yeah.
Study like the response we get at the very beginning, right?
Exactly. Yeah. So this would be maybe 365 days, right? And then a lot of things is temperature stability. And our setting down in the basement of our institute is because they have big air conditioning vents. So there is some temperature moving around, which is probably not the case in the big cave in the Ural Mountains, right? Yeah. Okay. So that's kind of maybe like almost like a crypto type of thing. Initially I said, oh, we can rotate, each mirror has 200 positions. So you rotate it by about 2 degrees, right? It turns out if you only move it by 2 degrees, nothing changes, right? So we did like a somewhat conservative estimation of the challenge place. We said, in order to really change that, you have to rotate by 45 degrees, a single one, right? And then you only have 8 position by mirror. So here you would then get a key space, if you wish, by 2 to the 60, which is not sufficient, but there's nothing magic about 20 mirrors. We go up to 40 mirrors, right? Or again, if that would be used, they probably would have 1,024 mirrors in some crazy thing, right? But the basic thing is good.
This just scales linearly.
Exactly, yeah. So this is good. This is really where literally Johannes, my PhD student, spent 2 or 3 years, right? How can we really attack that, right? So far I talked about engineering issues, right? So again, this is the setting here, right? And another way of thinking about it, if the Russian gets a challenge here, he can do 2 things, right? He needs the RI, right? The easy thing is don't fiddle with the warheads, leave the warheads in place, and then this computes RI, right? Through this physical setup, right? So you can model that as a function here. You get, and then this happens, or you do this, and now is the question. Now the Russians have to literally compute it, right? So, and now we get a formula in here, right? So the input, and again, I stress in that the input is a mirror setting, right? 20 mirrors in a certain setting, right? What is the RF fingerprint here? Very weird function, right? What is the function here, right? This is physics, right? Or maybe communication engineering, right? How do we do that? And then we have to do a prediction, because what the Russians have to do, I mean, should the Russians know the list of CIs, we've lost anyway, right? I mean, if you know that 1 second ahead of time, they can just, probe this rule here, right? Yeah, so we have to model a function, right? This is what ML is good at, right? There might also be other ways what the RF engineers do that doesn't work with like race tracing and stuff. So the most promising way that we see is really race tracing. So we learned a lot of applied machine learning. For instance, what we did here, we're not assuming 20 mirrors, but 12 mirrors, which is easier. There's less entropy in the room, right? And then we use different ML algorithms, and actually with neural networks, we could break it, right? So don't use 12 mirrors. This is what this slide said, right? And then we spend a lot of time. So they're a little confusing here. So this is maybe good. So what we did is we started with using 4 mirrors, which we can use. So 60 mirrors are untouched, and only 4 mirrors are turning, right? And then we trained a neural network. And what you see here, this is this line here, right? What you see, you go down after about 1,000, 2,000. With 2,000 training data, we could reliably train a neural network so that predicted the fingerprint, right? So you put in 4 mirrors, the positions, the ML model told you what the fingerprint is, right? Okay, now we go to 5 mirrors, so it's not only 1, 2, 3, 4, but the 5th mirror is turning 2. There's more entropy, right? The function, I'm going back 1 slide. This F is getting more complex, right? Suddenly you have 1 more variable, right? That's doing pseudorandom stuff here, right? So what happens? We have to go down here. This is 1,000, so it doesn't 1,000 feet. You need like 4,000 XY pairs, right, to train your model reliably. So what we could do is here, you see the same here, number of active mirrors. So up to 12 mirrors, we could actually model. And now if you go here, where do we end up? We needed something like almost 1 million traces, right? Which took like days to collect this type of thing, right? Yeah, and with the 20 mirrors that we propose, and then here, the big thing is this correct what we do, right? Is this line tracing, is this really going like that, right? Or is this suddenly going down? Because the maximum we could do was 1 million here, right? In practical terms, right? You know, we worked at the end with the ML part, we worked with people at Harvard together. They're better with ML, but that's probably a good idea, right? The nice thing is here that here is the number of active mirrors is linearly, and this is exponential. So that looks nice, right? So the whole, again, if you go up to 256 mirrors or something crazy, it's probably very hard to predict this thing. Yeah, and then we published that about 3 years ago, and there was a lot of work went into that, and we are very happy that this worked. Yeah, okay. So, and this is the advertisement slide because the second edition of my book came out, and we have a big bachelor program with like 800 students in cybersecurity, and our intro class is Intro to Cryptography 1 and 2. So thank you very much.
Back to the attack. So it seems that 20 mirrors you need to take 51 days to collect the data. It's not too long, right?
No, exactly. That would be, yeah. That's what, I mean, that would be using AES with 40 bits, right?
Okay.
Yeah.
So what is the suggested number of mirrors you
Well, I mean, it grows exponentially, right? So you would probably, if you go to, if you would go to 40, if you would double that would grow by
500 days, I guess.
by exponentially, right? That would by 7 orders of magnitude. So it would be by 10 to the 14. So that would be 10 to the 14. This is 2 to the 40, 2 to the 45 measurements, learning phases you have to do, right? And this is only 40, right?
Right.
And then, yeah. So I think pretty quickly with probably 128 or so, we would be lifetime of the universe, right? That it would take to train the neural network.
I see. Does the prover also has the control for changing all those configurations? Like,
Yeah.
I program?
Yeah.
Then can I, similar to the prover, trying to get all those response for a large space of challenges, in 1 year, and then
You mean essentially brute force attack?
something like that, and then whenever I guess the probability of having a challenge falling into the space that I've already probed, it will increase with the time, right?
Yeah, but because the easiest thing is we talked about this here at the moment. The effective key space, right? Where was it?
I guess I don't need to brute force everything. I just need to see if I can have one of the random challenge to be aligned with my configurations.
Yeah, but even here we have 2 to the 60, right? So that would be if you go to, let's say, 128 mirrors, that number would go up to that would be 2 to the 360.
Yeah. But
So right? So yeah, what is your chance that you pick? Yeah.
2 to the 80 challenges, and then the probabilities
Yeah,
that
but
you
it takes
have.
a certain amount of time to probe each challenge, so the point is that it takes too long and then you maybe do a reset. I thought it's like realistic.
Yeah, but millisecond is pretty slow if you do the back of the envelope, right? This is 1,000 per second.
The 80 is way bigger.
Let's say it's 2 to the 40, and then what is the probability of having one of
Yeah.
them?
One over
Yeah. No, I agree. If this is not big enough, I'm absolutely with you, right? If the challenge space is not big enough, but my point is, in practice, you would probably have 256 mirrors, and the challenge space is so crazily large. So even if the Russians constantly, as fast as they could, start collecting something, right, that will not happen. Yeah.
Also, we have
Yeah.
which is so first she said, thank you for the great talk. In the protocol, the verifier has to spend a day in the facility, so that means that the
Yeah.
location of the facility is leased. Do you think this is necessary? Have you thought of ways to avoid it? That's
Well, we did think about it because that's actually a good question. In reality, what we think the real world weakness of that protocol is the verifier has to spend 24 hours, right, in the facility, right? The Russians are not allowed to wiretap, right? So if they have hidden cameras, hidden whatever, hidden sensors, then the whole thing is void, right? And that's what I mean. I'm not a specialist. I would imagine as an engineer, there could be many sneaky things the Russians or the Americans, right? The same could also the Americans do, right? Can do because the whole thing falls apart if they know the challenges ahead of time, right? Yeah.
Two quick questions.
Sure.
The question is very simple. It's like these like waves that bounce on the warhead.
Right.
Do they rely on the material or only on the like volume of the warheads? Like, does the density of the material matter?
Not the density, but the like these whatever reflection coefficient, right? Like wood reflects difference in metal, this type of thing.
Right. So, but I guess the simple question is, could you replicate the same room?
Yeah.
With
There was an original paper by Uli Ruhrmeier who defines that notion of virtual proof of reality. And one big central requirement was non-clonability. So if you replicate the room one to one, we lost two. Yeah.
without warheads. Like
Yeah.
the second room.
Yeah.
Yeah.
But there are interesting things, and now when we do talk in the Nature paper, we talk about that. There are things, relatively easy things to make the room unclonable. For instance, now just to give you like a thought experiment, right? So you have the nuclear warheads. Also, another thing is maybe take the nuclear warheads out and put like a cardboard version of the nuclear this type of thing. Well, one way of randomizing that, so you have your nuclear warhead, and now you get your glue gun, hot glue gun, right? You put that on, and you also go to your Walmart store and buy one package of aluminum kitchen foil. And you crumble it, and now you put this crumbled thing on that. If you want to replicate, you have to exactly replicate the way this aluminum foil is crumbled on this one warhead, right? And they also actually, which I didn't know, again, there's this whole community of RF engineering. You can actually buy in specialized physics or engineering supply websites. They have like plates, they're pretty much the size of this blackboards there, but they're metal mesh. And inside the mesh, you have this random structure, kind of what I described as this crumbled aluminum foil, right? For these type of random environments, right? So that would definitely be somewhat of a maybe cat and mouse game. How do I prevent the Russians of replicating the same room? Yeah.
So this would require that this aluminum like
Yeah.
would happen at setup, right?
Yeah,
So the
exactly.
Americans would have to
Right.
to do that. Then my second question is
Mm.
relates to the setup phase. Is there a way that the Russians could like tamper? Because it's really important how you sample the randomness for the challenge. Like you need the
Yeah.
like random number generator.
Sure. If that's not true, if they can predict what the next challenge is, as you said before, because they have most of the time they have total control of the room, they have plenty of time to compute the fingerprint, right?
Oh no, but I guess the
Yeah.
question is like I suppose they use some sort of like seed, like
Yeah,
truly random seed to
right.
these. Usually, like these are either sampled by like truly random sources,
Yeah.
but those could be outside the room sources. Could those be part of the
If I were the Russian, I would look into all these attack vectors. Where do the Americans get their randomness from, right? But then you could argue, in order to prevent that, they collect their randomness before they fly out in the Pentagon, right? Highly secure, blah blah blah, right? Right. In SHA-3, yeah. Sure.
And so one question is,
Mm.
how tolerant is this to random issues, or is that a policy question afterwards? Like,
Yeah.
if there's an earthquake, for example, is that going to kill everything? Is that going to cause a problem?
Yeah, I mean, if the earthquake, let's say, if it damages the geometry of that storage space, yeah, probably. Yeah.
Then the second question is like, okay, if you're doing only the check after 1 year with the initial setup, that seems like maybe you could, after a year, put things back in place as they were, take very, very precise measurements, and after a year, everything is back.
No, we're probing every 10 seconds.
Oh, so you can keep probing.
We do every 10 seconds, right? I mean, again, I don't know. What about, let's say it's actually 10 seconds, right? Is 10 seconds, would that allow the Russians to take one in and out within 10 seconds, right?
I mean, that's a lot. So that seems like a policy question, but
Yeah.
but it is somewhat frequent. It's not
Yeah.
we do all of the queries
do.
all at one time after a whole year. That seems.
That's why we came up with that if you have 24 hours, and I think if you assume 1 millisecond per fingerprint, you collect enough fingerprints that you do for 1 year, you probe every 10 seconds, right? This is roughly the relationship.
That if you have a new one to be replaced in say 10 seconds, you can directly use that one without even putting it back in the room. If you have a
New warhead?
Yeah.
Well, but the point
Why
is you
not?
replace it with something else.
Yeah.
That-
But then we want to do the aluminum on
yeah. Clothing?
Yeah.
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 And then these antennas and stuff, how do you ensure that these are like good?
Well,
Like how good are these sensors? I mean, this is just a sort of
yeah.
curiosity.
But I mean, this is really the brilliance, this idea of if you're interested in that, I would actually recommend it, not so much reading our article, but the original article on virtual proof of reality that was CCS 2014 maybe. Because the normal way of dealing with that, right, in a less hostile environment, if you go back to that very first thing here, is why don't you put a security camera on, right? What is the Amazon camera? The house. Yeah, ring cam. Why don't you do that, right? Why do you do this thing, right? You always rely on a secret, right? Because then you need a cryptographic secret in that, right? The beauty of this setting is here, you just brought that up with the antenna. All of that is public, and you can tamper with them what you want. The Russians always lose, right? Whatever they change with that, they will not get better at predicting this here. So in that sense, you can't put hardware Trojans, which is something I'm working on. You can't put Trojans in here, blah blah blah. That will not give you any kind of advantage. It's kind of a very pretty setup in that, right? So there's no secret in the system, right? The secret is this physical setup itself. Yeah.
I also really like that you mentioned the S&P paper about server rooms, because one of the things, my advisor is super into SGX stuff, not me.
Yeah.
But one of the problems there is like pretty much all the known attacks on SGX, assuming you implement everything correctly and you do all of the correct cryptography, are physical attacks, right?
Exactly.
So could you now have the same setup but for SGX physical servers?
Yeah.
I mean, this seems like an interesting direction to explore
Yeah.
too, right? Because they're in these server rooms, it's not like one person or like one entity. Now you have like many individual people.
Right.
So how do you make protocols for that?
Yeah. I mean, this is James Bond. I think also like server room attacks are much more realistic, right? I know from way back, I did long time ago, I did some work on TPM modules.
Yeah.
And that's the same. I mean, as far as at least back then it was the assumption was all the proofs, right? That takes these software measurements, blah blah blah. Assume you don't do tampering attacks. That means the communication between the TPM module and the CPU can't be wiretapped, right? Now, if you can wiretap, essentially your model fails, right? So your security proof.
So TX stuff is actually fine because what you would say is like, well, you use encrypted channels and all that, so even if you wiretap it, it's fine. You use oblivious RAM on top, so that prevents like.
Okay, so they took care of that, but yeah, okay.
All the data coming out is encrypted, and even side channels where like access patterns are taken care of, but the device itself, the like trusted module, in this case SGX module, has some side channel leakage of like. And
you can probe with needles.
If you tamper with it.
Yeah. I mean, just in general, I think it's probably, I don't know whether it's possible to get absolute cryptographic guarantees if you, let's say, if an attacker has arbitrary access to your hardware, right? I mean, my intuition is that can be attacked, and then maybe you need this type of defenses. Yeah. And again, in most settings, it's not that hard because in most settings, the verifier has better control of this room here. So this is it's actually it's so extreme that when we wrote the paper, it was really hard for us to come up with another scenario with this setting, right? The one that exists, there's apparently in New York City, they have the storage space. I don't know who in the room here owns an original Picasso painting, right? Which is worth. You may not want to have that in your house, right? So you put that in storage space here. And that is similar, right? So this is whoever in New York runs this storage space, right? And now it might be of interest to you to check whether your Picasso painting is actually there, right? Without flying to New York, every month or so. But that's stupid, right? This is a super edgy, niche application, right? So we couldn't come up with many other good examples for that, right? But what you said, I think server room, this type of thing where
especially the trusted modules where all the known attacks are hardware.
Yeah, exactly. Yeah. But that I think the other paper was much more practice relevant, where we temper detection against small enclosures is a big thing. Another thing in Germany where we live, because we live in northwestern Germany, which is next to the border to Netherlands, there's this really, I don't know, funny, bizarre crime wave by Dutch criminals. So they drive over the border, they're all the high-speed autobahns. They pump gas in German ATM machines and they explode. They literally explode and they take the cash and they race with the Porsches back to Holland, right? This is like the crime wave in northwestern Germany. So here it would be, how do we detect in an ATM machine that there is gas being blown in, and you could probably use something. Well, they try that. I mean, they have color, right? It's colored, but apparently, I mean, it's still, they have dozens of these per year, right? And again, the state where we live, North Rhine-Westphalia, is on the border, so it's kind of it's a little funny, right? Also, the Germans haven't come up with. But here it would be as soon as you detect gas, like a big alarm goes off and the police is alerted, this type of thing, right?
No, but if there's somebody who's like pumping anything in, right? Like you only want things to come out, essentially, unless there's somebody with a key who's like opening it.
And then refresh it.
Okay. Thank you so much.